Members of the presidency, authorities, esteemed co-laureates, distinguished guests, John Hennessy and I are very grateful to the BBVA Foundation for this prestigious award, and to the jury of our colleagues who selected us. We were thrilled to receive it. I deeply regret missing this beautiful ceremony. To understand our contribution, we'll explain some jargon. When software talks to hardware, it uses a vocabulary called an instruction set. Examples of words or instructions in the vocabulary are on the keys of a calculator: add, multiply, and so on. Programs consist of millions of these simple instructions executed billions of times. Hennessy and I were assistant professors in 1980, and conventional wisdom was that many information technology problems were due to computer vocabularies being too low level. These instruction sets supposedly placed a large burden on programmers, leading to software bugs and failed software projects. The prevailing philosophy was to raise the level of abstraction to create vocabularies of complex instructions to reduce the gap between people and machines. In the 1970s, microprocessors were only found in home appliances. Hennessy and I believed in Moore's law, the remarkable prediction that the number of transistors per chip would double every year or two. We were convinced that microprocessors would become the foundation of all computing. The question was, what was the best vocabulary or instruction set for these rapidly improving microprocessors? Should it change from the large computers that powered the industry of the 1970s? To answer this critical question about the interface between software and hardware, we need more context. It was so tedious to program in the low-level machine language that computer pioneers soon invented high-level programming languages that were easier to use, plus programs that translated from high-level languages to machine language, called compilers. While high-level languages were popular for many tasks, conventional wisdom was that compilers were too inefficient to use for some software, such as operating systems. The success of the Unix operating system in the late 1970s, written in a high-level language, changed people's minds. Regarding instruction sets for microprocessors, the programmer's burden of writing in low-level machine language was no longer an issue. Instead, what was the difficulty for compilers to produce high-quality machine language programs? We called the large computers with vocabularies that followed conventional wisdom complex instruction set computers, abbreviated CISC and pronounced CISC. We proposed that microprocessors should instead use vocabularies with simple instructions, which we called reduced instruction set computers, abbreviated RISC and pronounced RISC. Think of complex instruction set computers as having many polysyllabic words, while reduced instruction set computers have monosyllabic words. Hennessy and I thought it would be easier to build microprocessors that understood reduced instruction sets vocabularies rather than complex instruction set vocabularies. The question then was whether RISC or CISC was faster. While a program might have to read fewer instructions using a complex instruction set computer, since the instructions were more sophisticated, that might mean that the average instruction would take longer to read and execute than a reduced instruction set instruction. The analogy is that a page filled with polysyllabic words might take longer to read than a page of mostly monosyllabic words. This seemingly clear scientific question was emotion-packed in the computer design industry, which we call computer architecture. The complex instruction advocates believed that the reduced instruction set computer was a step in the wrong direction and would add complexity to software. The RISC advocates thought that was an out-of-date argument and that compilers could hide those differences so that programmers couldn't tell the difference. While Berkeley and Stanford are rival institutions, much like Barcelona and Real Madrid are in football, Hennessy and I both realized that we should join forces to argue for reduced instruction set computers. An international conference held in Silicon Valley in 1982 organized the first RISC versus CISC debate. Heated conversations continued into the hallways afterwards and lasted long into the evening at that event, with several more debates over the next year or two. Max Planck said that scientific truth does not triumph by convincing opponents and making them see the light, but that science advances one funeral at a time. Fortunately, in computer architecture, there's a companion industry that tests our ideas in the marketplace, so we don't have to wait for funerals to change the field. To answer whether RISC or CISC is better, we needed to discover the ratios of the average number of instructions a program needs to read. Complex instruction sets should be fewer than reduced instruction sets, versus the average time to read one instruction. RISC instructions should be faster than complex instructions. We ultimately discovered that RISC reads a few more instructions than CISC, but it is so fast that the net result is RISC is 3 to 4 times faster than CISC. Moreover, RISC microprocessors needed much less hardware than CISC microprocessors. These advantages are borne out in the computer marketplace, with the RISC processors doing very well in the late 1980s and early 1990s. Intel had a CISC architecture that powered the IBM personal computer, which was a very valuable franchise. They also had the world's best semiconductor manufacturing, at least 2 years ahead of everybody else, which meant that at least twice as many transistors according to Moore's law. Remarkably, they used those extra transistors in the microprocessors to translate from complex instructions into reduced instructions in hardware internally billions of times per second, so that they could execute the old programs but run at RISC speeds. Intel's RISC in CISC clothing dominated the personal computer market and eventually larger computers through the 2000s. The iPhone in 2007 relied on RISC and opened a new market that grew much larger than personal computers. As power became the major limiter in chips, and as Moore's law began to slow down, the efficiency advantage of RISC, both in transistor use and power, that led to its use in the iPhone became even more important, propelling it to an even more dominant position. For the past decade and for the foreseeable future, 99% of the microprocessors in the world use RISC. Wrapping up our story, computer architecture is a team sport, so the BBVA Award is recognition for our wonderful collaborators and former students at Berkeley and Stanford as much as it is for us. We also thank our spouses and families for 50 years of support from graduate school through our long research careers. We certainly couldn't have helped make these contributions without them standing by our sides. Thank you once again for this high honor, and I once again wish I could be there with you celebrating this event. My longtime collaborator and good friend John Hennessy will tell the rest of our story, which is how the RISC advance led to startup companies and inspired a revolution in how computer architecture is taught. Thank you very much.